Okay, good afternoon, good morning, whenever you're tuning in. If you missed 7.08, it was an assignment where we went on kind of an exploratory assignment where you made some predictions based on probability, ran some simulations, and you kind of expanded on those. So I'm going to give you a run through if you missed it, just kind of walking through the process that I would do to make the most, that makes the most sense to me. Now, what I didn't do, as you can see on my screen, is I forgot to complete those steps for you. I'll complete those steps and I'll fill those out with like a step-by-step process of how you do it to refer back to after the video. But right now, let's just open up an assignment and take a look. So I'm going to go to somebody's screen, student work. Let's go to, Michael, you're at the top. If I hope you don't mind that I'm using your work. If you do, I'm sorry. Please forgive me. If you don't, you're welcome. And what we have here is some charts where we're talking about theoretical probability, making predictions, experimental probability, et cetera, et cetera. And we have to fill out these charts for each different event. So the first one is just rolling a single die, one 6-sided die. And we want to calculate the probability and, you know, really make some predictions based on what that probability is telling us. So the first thing we're going to do is actually calculate that probability. So this says probability of finding or of rolling a 2. So you would think first, how many sides on a dice have the number 2 on them? Well, you got a 1, a 2, a 3, 4, 5, and a 6. So only one of them has a 2. So our theoretical probability is 1 out of, well, how many total options do we have of when we're rolling a dice? So 1 out of every 6 because there's 6 sides on the dice. So you have a 1/6 chance of rolling a 2. So I know this looks a little funny, but that's just the probability of rolling a 2. So we have a 1/6 chance. Theoretical probability is just probability. So you can then go ahead and find the theoretical probability of rolling an even number. So think about how many dice or how many sides on a die have even numbers. How many total? 6 different sides, right? So something over 6 and then something over 6, right? Each one of these are going to have a denominator of 6. Well, because if we're rolling one die, there's only 6 possible results. And we're going to make a prediction of basically, if we were to roll this die 200 times, how many times do you think we would land on the number 2? So how many times do you think we would land on the number 2 if we rolled it 200 times? Well, in order to do this, all we need to do is multiply our theoretical probability, 1/6. Oh, you can convert it to a fraction for me. Oh, nice. Times 200. And we can do that on a calculator here. I'm just going to do that myself. Just double check, make sure that I don't give you a funny answer. 1 divided by 6 times 200. And I get 33.3 repeating, which we wouldn't put in there. So basically what we would say is if we were to roll a die, one die, 200 times, just count how many times we roll it and tallied up how many 2s, 3s, 4s, 5s, we would expect the number 2 to come up 1/6 of that time, or approximately 33 times. Okay, so we used our theoretical probability. We multiplied it times how many rolls. That tells me 1/6 of 200, which we would say is around 33 times. So now that we have our theoretical probability and our prediction, the next thing we're going to do is run an experimental probability. Now, experimental probability is our simulation. So I'm going to put a comment in here. Here's our simulation. So experimental means that we are going to observe the outcome of a simulation or a real life happening. So what I've done here in this is I've actually included something, this dice roll simulation software, in the assignment that you can go to. And you can see that you have 2 dice in here to start. Let's go down to just 1. And you can see our total number of rolls here. I can count by 1s up to the number of rolls, right? And I can roll my die, you know, that many times. Or I can roll my die like 10 times at a time just to speed up that process. You know, and I can do that a whole bunch of times. Or I can just hit 100 twice. Bam. So this kind of fakes it. Like this is a, you know, they have an algorithm in this computer that allows, you know, probability to take place as close to normal as is possible. And one of those events of rolling it 200 times would look like this. We had 31 1s, 29 twos, 26 threes, 43 fours, 35s, and 41 sixes. That's a total of 200. And what we want to know here is the experimental probability out of those 200 rolls of rolling a 2. So let's look. How many times did we get 2? 29 times. So our experimental probability was 29 times out of that 200. I could put that as 29 over 200, but we know that the common denominator for both of these is going to be 200 based on 200 rolls. Now, what I do want to do is I do want to insert a picture of my simulation. So you can see down here that we want to insert a picture of our simulation. So I'm going to go to this, and you might have a screen grab. Let's see if I do. Control-Shift, Windows. Nope, that didn't work. All right, so I've got to use actually my snipping tool. And let's see, just kind of snip that. I'm going to hit copy, and then I'm going to go to my document. You're welcome, Michael. Hopefully you appreciate this. If you don't, you can delete it and do it on your own. And I can just include a copy of that. This is proof that I ran a simulation. Now that I have the simulation, I can do the same thing for these three. Find the theoretical probability of rolling an even number, predict how many times I'd roll an even number out of 200, and then go ahead and count up how many even numbers I have in my rolls. And hopefully what you notice is that your prediction, although it might not be perfect, is a pretty good measure for how close we're going to get on our experimental or our simulation. 33 times versus 29 out of 200, those numbers are pretty close to each other. So our predicted value using our theoretical probability was very useful. So you're going to go through and you're going to finish these three columns using your simulation. Now, I put a prediction over 200 rolls here, but what I really wanted you to do was make a prediction on 1,000. So please change that number and then run an experimental probability for that 1,000. So now that I've done all of my work down here and cropped my simulation, now I can run this up to 1,000 rolls. Well, what is 1/6 of 1,000? If I roll 1,000 times, I'm just going to do 1/6 times 1,000. And if I do that, I get 166.6 repeating. Okay, which let's just write that as roughly 167 times out of 1,000. So if we completed this simulation to 1,000 rolls, we rolled a die 1,000 times, we would expect it to land on the number 2 167 times about, somewhere around there. So we can go to our same simulation. Now you can either reset or you can kind of keep building. But let's run that on a new simulation up to 1,000. And you can see we've got a lot bigger numbers now. That's okay. So what is our probability of landing on a 2, right? How many times did that happen? 177 out of 1,000. So I'd come back, I'd say 177 times. Yeah, I could put 177 out of 1,000 times, or I could just write 177 because each one of these is talking about 1,000 times. And what I should see again is that my predicted value, 167 versus 177, even though they're only they're 10 off, those numbers are still pretty close to each other when you're talking about, out of 1,000 rolls. So once again, my prediction was fairly accurate. Okay, if we do this over and over again, we're going to get different numbers on our experimental. Obviously, this is going to change. And we should see that, our predicted versus experimental values should be around the same. And really, the more times that we run this experiment, if we ran this to, 10,000 rolls or 1,000,000 rolls, we would actually see those theoretical and experimental values start to approach each other in a very close way. So before I go on and talk about the next section, I'm just going to make sure that I get a screenshot of this. You can do this on your phone if you don't know how to screen grab, or you can just Google it, how to take a screenshot on my Chromebook. And let's go there, and Michael, once again, doing a lot of stuff for you. Now you won't have to run any simulations. So I'll have my 200 and 1,000 roll simulations for each one. And, I can use now those simulations to fill out the rest of these. But what you're going to have to do first before you do that is, of course, calculate your theoretical probability for each of them. Now, that was the first day of this, where we actually went through and we, ran our simulations, we found our probabilities, et cetera, for one single die, a single dice roll. Now, casino games or dice games in general typically have 2 dice. Okay, so what I wanted to do is I want to talk about how does the probability change for rolling 2 dice? And now our denominator is no longer going to be 6, because if you think about all of the options for rolling 2 dice. We no longer just have 6 options, 6 outcomes. We have many outcomes. And you might be thinking, well, you can add those dice together. And actually the lowest number you can now have is 2 for rolling a 1 and a 1. The highest number you can have is 12 from a 6 and a 6. So you might be thinking your denominator is actually 12 because there's 12 possible numbers. But that's not actually what your denominator is going to be. For all of these, your denominator is equal to 36. And the reason why it's 36 is because there's actually 36 different combinations of those 2 dice. You know, I got 6 on one and I got 6 combinations on the other. So due to that multiplicative property, 6 by 6 is 36. That means there's actually 36 combinations. And I actually put a diagram in here. And this diagram, if you can see this, shows all those combinations. The only way to get a 2 is a 1 and a 1. The only way to get a 3 is if one of your dice is a 1, the other is 2, or vice versa, right? Or maybe if I'm rolling a black and a white die, they switch where one is a 2 and the other one's a 1. Okay, so a 1 and a 2 and a 2 and a 1 both give me a 3. Whereas for a 4, I got a 1, a 3, 3 and 1, and a 2 and a 2. Right, so you can actually see that the probability for each one of these numbers is somewhat different or changes. And you can see that there's a lot more combinations for the number 7 than there is for, say, you know, the numbers 2 and 12. And that number 7 is pretty loaded with possibilities. I could roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, a 6 and a 1. So we can see that there's actually 6 different combinations, 6 different ways to roll a 7. So if you want to think about writing a table here, the probability of rolling a 2, let's see, is 1 out of 36. The probability of rolling a 3, let's look at my table, is, now you can use the decimals or you can use over here on these fractions on the side. I like using the fractions. Fractions make more sense in this scenario. So if I see the number 3 and I go over, that's 2 out of 36. Oop, let me use my marker. Okay, and we can continue just kind of writing these down if we want. Probability of rolling a 4 is 3 out of 36. And we can see that there's definitely a pattern here. Okay, all the way up to the probability of 7 has the highest probability, which we said was 6 out of 36. Okay, and then we can see that it goes back down. The probability of 8 does not get any higher. And if you think about rolling 2 dice, okay, here are all your combinations. That's 5 out of 36. And then, of course, it decreases again all the way back to the probability of 12, which is just one combination, which would be a 6 and a 6. So these are all of the different probabilities. And once again, we can see that the probability is changing, but we can see that the probability has the same denominator of 36, because if you add up all these possibilities, there's 36 different ways to roll 2 dice. So keep this in mind, because now when I clear this, we're going to go back and we're going to take a look at how can I, find the probability of rolling a 5. Well, if you look back at that again, the probability of rolling a 5, let's see, was 4 out of 36, a 4/36 chance, because there's 4 different combinations. So that's going to be my theoretical probability. So I'm using that diagram to help me. Maybe I'll put a note in here. Use the diagram in the assignment. Okay, they've done all the hard work of running that probability and listing all those possibilities out for you, so use it. So now, of course, we're going to do the same exact kind of thing. And of course, we want to make a prediction for 1,000 rolls over here. And so we're going to make a prediction of 436 times 200. And we're going to see, okay, if we roll 200 times, what's the probability of rolling a 5 out of those 200 times? So out of those 200 times, we get 22.2 repeating. 22.2, which we would say is, approximately 22 out of 200. So that kind of gives us an estimate. And then, of course, we would want to run the experimental probability again. So we just go back to our dice roll, and we'd switch this to 2 dice. And since we want 200 rolls, I hit that 200 times. And we can actually see that the curve is actually looking a little bit like the curve that we noticed here. There should be a few more rolls in the middle. It's not perfect because probability doesn't always work out perfectly, but it does kind of show a discrepancy in the probability. How many of those rolls were 5 out of 200? 13. So let's go see, okay, we had 13 times. That was our experimental probability. And then once again, I'm going to make sure to screenshot this. So that we can refer back to it. And then I have proof that I've actually done that probability. Or done that simulation, okay? Now I can use that same simulation to, first predict using what's my probability of 12, make my prediction, look down to my experimental 5 out of 200. 6, 7, or 8, same thing. Now this time the word or comes up, so I'd be adding some different possibilities there. And then of course you're going to do your prediction experimental for 1,000. So you go back, go to 1,000. Oh, I went over, so I'd have to reset that and go back to 1,000. No big deal. Bang. Okay, and you can actually see that as we roll more times, our diagram here starts to look a lot more or resemble a lot more closely this diagram that I showed you before. So this is us using, probability to make predictions and then actually running a simulation to make some comparisons. So that's kind of what I'm leaving you to do and leaving you to notice. So it's up to you to now finish the rest of this. You can use the work that I have, but finish the rest of this and submit it for that quiz grade so that I can get you some maximum points.